thought I will deliver the last lecture, but it's been a long time, and in that long time many people have asked me what is the difference between the way you pair loops for a plant wide control system and the way it is conventionally done. And so I think it will be appropriate to highlight the differences so that it is clear to the audience as to how it is done and how we are doing, and then people can make a choice as to what is appropriate where. Before I do that, I must highlight that conventionally constraints are handled using overrides, and it's best done as an illustration. For example, let us say I have a simple distillation column, and it's got a certain feed rate that needs to be processed. And let us just say that I am told maximize throughput. So conventionally what is done is you have your throughput manipulator is here, this is set probably by an upstream process, and the conventional way of doing things is this is under pressure control, this is under level control, I just say this is under temperature control. This is the conventional way of doing things, and let us just say this level is controlled by adjusting the bottoms, and let us just say the product composition is being controlled by adjusting the reflux. Okay. This is the way conventionally this process would be. This is the conventional control system on this distillation column. Now let us say the idea is to maximize throughput. If I want to maximize throughput, this flow into the column will increase, and as it is increasing, let us say the constraint that goes active is the column starts getting flooded. So if the column is getting flooded, that means that you are putting in too much boil up, there is too much vapor traffic, and because of this vapor traffic the liquid on the trays is not able to fall down, and therefore the liquid starts getting stuck on the trays, and this is called flooding. So when you are trying to maximize the feed processed, if that is your objective, you find that the maximum amount of feed that can be processed is limited by the flooding limit of the column. So what would be done is that you have a maximum limit on the boil up, and let us say there is a boil up controller here that is adjusting the steam. This boil up cannot go beyond a Vmax, a maximum boil up, because beyond this boil up the column gets flooded, and then what I have is a low select, and my temperature controller is setting the boil up. Now what happens is the temperature controller is setting the boil up, but if temperature controller is asking a boil up that is beyond the flooding limit, that means the temperature controller output is beyond Vmax, then the lower of these two signals, between these two signals the lower one gets selected, and now temperature control is lost. Well, if temperature control is lost, then what will happen to the bottoms? What will happen to the bottoms is too much of the light key will start to leak down the bottoms, the light key will increase. So you will lose the control of light key dropping down the bottoms because temperature is uncontrolled. Because temperature is uncontrolled, too much light key will leak down the bottoms. That means your column will lose too much of light key down the bottoms. Now let us say that light key, let us say the bottom stream is a waste stream, and let us say the light key is precious. Then what that means is, since too much light key is being lost, it is an economic loss. So what that means is I do not want to lose temperature control on the column. What do we do then? Well, conventionally what is done is, you have, let me put it, well, let us not worry about the colors. You have another temperature controller, and I am calling it OTC, override temperature controller. And what this temperature controller does is, it adjusts the feed. I will put a low select here. This is the operator setting the feed. Well, let us see. This is the operator setting the feed, or an upstream process setting the feed, and the other signal to the low select is from this. Okay. And now the set point of this temperature controller SP2, and let us say the set point of this controller is SP1. What we have is SP2 is slightly less than SP1. Okay. So, now imagine when the boil up is unconstrained, that means the temperature is, the boil up is unconstrained, then temperature controller, the nominal temperature controller will be controlling the tray temperature, and therefore, what will happen is, well, let us see. Okay. So, for the override temperature controller, temperature will be greater than SP2. Because temperature is greater than SP2, the override temperature controller will say that, look, my column is too hot, give me more feed. That means this signal will be, the output of the temperature controller will be large. This implies its output would be large, because the override temperature controller is saying that, look, the actual tray temperature is higher than my set point. So, put in more of the cold feed so that the tray temperature comes back. Okay. Now, because this output, this signal is large, this would be greater than the the flow set point that is being set by an upstream process or by an operator. Okay. So, because this is greater than that, the feed is being set by the upstream process. This signal goes through, this signal goes through, and therefore, the feed is being set by the upstream process or by the operator. Now, let us say the operator or the upstream process is increasing flow set point. What will happen? The sequence of events, if the flow set point is being increased, you are putting more feed to maintain the tray temperature, the boil up will go up. As the boil up is going up, this signal will keep increasing. Ultimately, this signal will become greater than V max, and therefore, at low throughputs you had this signal going through. There will come a stage when this is what will go through, and now temperature control has been lost. Because temperature control has been lost, you cannot increase the boil up anymore. So, the tray temperature will start to go down. Now, as the tray temperature is going down, ultimately the tray temperature will cross set point 2, it will go below set point, and once it goes below set point, now the override temperature controller says, well, the temperature is going down, that means I am putting in too much feed, I should be putting less feed, and this override temperature controller will now start to decrease this signal that is going, this will start to decrease. As this starts to decrease, ultimately this signal will become lower than the input set point by the operator or by the upstream process. Okay. And then what will happen is, instead of this signal going through, what will happen is it is this signal that will go through the low select. Okay. So, now my control structure has changed. If I see what is happening, my control structure has changed to V max being constant. My control structure has changed, V max is constant, and temperature is getting controlled by the feed. Okay. So, this is an override scheme that cuts the feed when the boil up becomes maximum. So, I think it is important to show this again. How do we go back? Okay, so we were talking about the override temperature control scheme, there was some technical glitch. So, what I wanted to say was that when I am running at low throughputs, what I have is at low throughputs. So, let us see pen, let us see low throughputs, ink color is let us say blue. At low throughputs, flow is fixed and temperature is controlled this way. Once the throughput goes high, then once the throughput goes high, V1 goes maximum. So, therefore, V1 is fixed and temperature is controlled this way by adjusting the feed. Do you see how these low selects actually end up altering the control structure when a constraint is hit? Okay. So, the override the disadvantage of this scheme is the fact that SP2 must be less than SP1. So, SP2 must be less than SP1. Why does it have to be less than SP1? So, that when temperature is being controlled by the boil up, when this loop is on, I do not want the override temperature control to be adjusting the feed. So, that will require that the set point for the override temperature controller be sufficiently away from SP1. What that means is when this override scheme takes over, I will have greater loss of light key down the bottoms, because the temperature set point when throughput is increased, this controller takes over, and now the tray temperature set point here, the temperature operating temperature at high throughputs is less than the operating temperature at low throughputs. So, when TSP2, when this is active, TSP2 is less than TSP1, and what that means is that once the override temperature controller gets activated, my column tray temperature would be lower. The fact that my column tray temperature is lower implies that I will be having more leakage of my light key down the bottoms. The light key, what this means is light key leaking down, light key loss will be greater than light key loss at SP2 would be greater than the light key loss at SP1. So, what this is saying is that in my control scheme, in this override control scheme, at higher throughputs I will have more loss of my precious light key down the bottoms. Okay. Now let me take this a little further. Okay. Let us say this flow set point out here, the feed to the column, let us say this is being set. Let us say there was an upstream tank here, maybe it was a reactor, I do not know. Okay. And what was being done was that this flow set point, see, okay, this flow set point, the outlet of this tank was flowing into the column, okay, and ordinarily what I have is, I have my level controller adjusting the outlet. Okay. Since the level of this tank has to be controlled, what I will have is ordinarily, well, again there will be a low select here, and I will tell you how that is done. Let me draw it and then I can explain it to you later on. I have an override level controller. There is a flow controller on the feed to the column, okay, and I am setting the feed set point, and I am comparing it with the override level controller set point. The lower of the two signal sets the feed to the reactor or the tank. Okay. Now let us see how this works. Now ordinarily what will happen is, operator ordinarily, this is how things would go. The operator is setting the feed to the tank or the feed to the process is set by the operator. Okay. Now let us say the instruction comes, jack up throughput. He keeps on jacking up the flow set point, and what happens is, as the flow is being increased, the boil up becomes max. Once the boil up becomes max, temperature, the override temperature controller takes over manipulation of the feed to the column. Okay. Now that it has taken over manipulation of feed to the column, I do not have level control on the tank. See what is happening? Once again, let us see red color. So, once this gets activated, my level control is lost. I lose level control because the level signal is the output of the level signal is not going through. Okay. So, since level control is lost, what will happen is the level of the tank will keep rising, and as the level of the tank is rising, the override level controller, please show the picture, the override level controller will basically say, this guy will say decrease the feed, and ultimately what will happen is this signal will go below the set point being set by the operator, and therefore what will happen is you will have this guy going through. So, do you see how it works? Once V1 max goes active, once this goes active, temperature control is lost, temperature starts to go down, and in order to maintain the temperature, the override temperature controller takes over manipulation of the feed to the column. Once the manipulation of the feed to the column has been taken over, level control of the tank is lost, therefore the level starts to rise, and then the override level controller says cut the feed, and ultimately its signal goes below the set feed rate, and therefore the manipulation of the feed to the process or the feed to the tank passes from the operator to the level controller, to the override level controller. If there was another stream, another unit upstream, we would have a similar scheme. If there was something else, there were some units upstream, you know, the material balance structure will have to be altered all the way up to the process feed. So, this is how what should I say, this is how constraints are handled in practice. We are actually handling only one constraint. If Vmax goes active, material balance is altered all the way up to the feed. This is how things are done in practice. So, now I want, since many people have been asking me how is the pairing approach that we are recommending different from what is done conventionally, I thought it is good to contrast it and then take a few examples to show how things get done conventionally and how we are doing them. Okay. So, let us take the conventional, let us take the conventional approach. In the conventional approach, you see, you have conventional, what I would call our approach is economic, where we have discussed this many times, but many a times, but basically what we are trying to do is, in any process you put a control system Why do you put a control system? You put a control system so that all things that can drift do not drift. What are the things that can drift? It is basically inventories, and when I say inventories, I mean tank levels can drift. If you are putting in too much gas and taking out less gas, then the pressure in that system will build up. So, gas tank levels, gas pressures can build. Similarly, we have also seen that if what you are putting into the process is not being consumed by reaction and has no place else to go, it will build up in the recycle. So, component inventories in the recycle systems in recycle loops build. So, when I say inventories, I mean liquid inventory, I also mean gas inventory, I also mean component inventories, and we could, in the most general sense, we could also include energy inventories. You see, what does the cooler, what does the reaction heat removal mechanism on a reactor do? It basically removes the energy released by reaction. Now, it is the job of the control system to ensure, you see, you must have seen this equation so many times, accumulation of whatever, of material, of component, of energy is equal to in minus out plus generation. Okay. When we are designing a control system, let us say what we are doing is setting the throughput, you are setting how much, what is being fed into the process. Now, depending on how your reactor is operating, that also sets the generation. Now, our job in a control system is to make sure that the out term is such that it matches in plus generation. If the out term does not match in plus generation, you can rest assured that there is some kind of an accumulation that is going on, and this in that very simple tank example was, if I do not make sure that the inlet feed, let us say I am flow controlling the inlet feed, and let us say I am controlling the, so if the outlet does not exactly match what is being fed in, here there is no generation term, this level controller is basically ensuring that whatever is being fed in, the level controller ensures that exactly that same amount is being fed, is being taken out, so that accumulation gets driven to 0, so that your process settles to a steady state. Now, this basic logic or this basic rationale is applicable to all quantities, and in material and energy balances you would have seen that you write an equation for material balance, an equation for energy balance, you also write equations for component balance. When you are writing that equation implicit, and if you are saying that the left hand side is 0 and you are looking for the steady state solution, implicit in that is either in is matching out or out is matching in, and that is what the job of the control system is, to make sure whatever you are putting in either gets taken out or gets consumed by reaction and does not build up in the process. Okay, so this is the whole thing that a control system does. So, one way of looking at a control system is, it is basically ensuring or balancing process inventories. What are the process inventories? In the most general sense, you have liquid, you have gas or vapor, you got components, and you got energy. My control system is basically making sure that all these inventories held within the process do not drift. Okay. Now, it so turns out that some of these inventories are economically more important, while the others are not as important. For example, if I take a reflux drum on a distillation column, its level makes does not affect the steady state of the column at all. Let us say I am doing it this way. So, on this reflux drum, what is the set point for this chap? Really does not affect the steady state at all. Because it does not affect the steady state at all, it has no steady economic impact. Okay? Yeah. So, there are things, so this has no economic impact, this has steady impact, no steady state effect, no steady state effect, and because it does not affect the steady state at all, it has no economic relevance to, at least for steady process operation. Yeah. So, well, so that is that. On the other hand, if I take that same distillation column that I had looked at, well, did I, yeah, we were saying that what is going out here, what is leaking out here is the light key, okay, and let us say this stream is actually a purge stream or a waste stream, and let us say the light key component is my product. Okay. Now, if the light key composition going out in this waste stream increases, what that means is I am losing out precious product. Yeah, I am losing out precious product which I am not able to sell. So, the inventory or the leakage of the light key down the bottoms of this column has a significant economic impact, because for every mole of product lost down the bottoms, I would have consumed that much extra raw material to produce that product, but now I am not able to, because the leakage is more, I am consuming extra raw material and I am getting no economic benefit. So, this is the inventory. So, the inventory of the light key leaking down the bottoms is actually economically significant. Yeah. On the other hand, what is the level here? Oh, I did not draw this, but yeah, what is the level here? What is the level here does not really make any significant, any steady state effect, and it is economically insignificant. So, you see, between the inventories, there are inventories that are economically important because they have a large steady state effect, because basically, and it has got to do with material loss. You would like ideally that all the raw material that you are taking in, because raw materials are expensive, all of it gets converted to products and none of it goes out in waste streams, because the waste streams actually do not fetch you any money. Okay. So, what I am saying is, if you think of it this way, then there are inventories that have no steady state effect and economic significance, and there are other inventories that affect my process economics big time. Okay. And what I really want to do is basically, okay, when I am designing a control system, I am basically wanting to make sure that the liquid inventory, the gas inventory, and component inventory and the energy inventories do not build up. Yeah. But it turns out that liquid levels in surge drums, not in reactors, because the level in a reactor does affect the steady state. Levels in surge drums, pressures in surge vessels actually do not make a significant impact on your economics. So, therefore, our approach is basically saying that, look, you have to control all the inventories. Okay. If you have to control all the inventories, what we are basically saying is control those inventories that have a significant economic impact tightly. So, first pair loops for tight control of economically important inventories. Okay. Then pair loops for the rest. That is the basic order, that then pair loops for the rest. how are things done? How are things done in conventional practice? In conventional practice, what is done is, if you look at, okay, for the rest, and these rest include levels, for example, levels and pressures, etc., etc. Okay, how is it? How are things done in conventional, in the conventional pairing approach? Well, usually what is done is the throughput manipulator is chosen at the feed to the process. Material balance control is then implemented, basically levels and pressures, loops for material balance control, and then finally loops are put for material balance control, total material balance control. Then you start putting in loops for component inventory control. And as it turns out, it is the component inventories in leak streams or in purge streams that are economically significant. It is the inventory of the recycle rate that affects your energy consumption. It turns out that actually these are economically more significant. Many of these component inventories are economically significant. And so, in the conventional approach, because you are pairing loops for material for control of levels and pressures first, what happens is the valves that remain for component inventory control may actually not give you the tightest control, because material balance control has already taken up loops. Okay, and it is this basic difference between the two approaches. In the conventional approach, you are pairing loops to avoid drifts in variables, which are the total material, the total level, the total, for example, the gas pressure or the column pressure, which really do not affect the steady state at all and which are economically irrelevant, have no economic effect. Because you are doing this first, the valves that get left for controlling the inventory, the component inventories, are not dynamically the fastest, and because dynamically they are not the fastest, what you will basically end up with is less tight control of the economically more important inventories. Okay. In our approach, what we are doing is we are controlling, we are pairing loops for the tightest possible control of all inventories that are economically important, and then we take care of things that have only a regulatory significance, no steady state or economic significance. That's the basic difference in the two approaches. And instead of blabbing a lot and trying to convince you this way or that way, what I think I should do is take you through a simple example. This is actually a complicated example. May not be this. Let's see. Let's see a simple. Oh, yeah. Let me take you through a very simple example. This is the Cumene process. If you count the number of valves, it's actually, I don't know, 1, 2, 3, 4, 5, 6, well 7, 5, 5, 5, 15 plus 7, there is actually 22 valves. Okay. This process has got 22 valves. Well, now if I look at the levels, I would like to, the columns have got 6 drums, the columns have got 6 levels, and these have no steady state impact. Also, I would like to operate the columns at the given pressures. So, 3 column pressures which are given, 6 plus 3 is 9. Is there anything else? Yeah, I would like there is a vaporizer level here, this level out here, this also is just a surge level, it has got no steady state relevance. So, column levels 6, column pressure 3, vaporizer level 1. That takes away 10 valves, 10 things that can drift, but really their drift does not affect my steady state. Therefore, 10 valves will get used for controlling these things which have little or no economic significance. Alrighty. If 10 valves go, what I am left with is 12 things that can affect my steady state. This is the steady state operating degrees of freedom. And now I say okay, I will optimize these 12 degrees of freedom for a given throughput. So, if it is a given throughput, I am left with 11 out of 12, 1 is setting the throughput. Now 11 degrees of freedom remain. I optimize these 11 degrees of freedom to, for example, maximize my operating profit for the process. Okay, this is what we have been doing. And now if I, so I have got 12 operating degrees of freedom, throughput is fixed, that leaves 11 degrees of freedom. Those 11 degrees of freedom or 11 decision variables are optimized to maximize my plant operating revenue. Okay. By the way, let me explain the process too. What we have basically is propylene alkylates benzene to give you cumene. Cumene is my desired product. The cumene can further alkylate, get alkylated by propylene to give you diisopropyl benzene, which is C12, and this C12 is not desired, you cannot fetch any money for it. This is my desired product, C12 is undesired product. So, I would like to ensure that my process is operated in a manner such that C9 is maximized and C12 is as small as possible, because C12 cannot be sold. It is any C12 will consume reactants, but I do not fetch any money for it. On the other hand, any C9 that I produce will fetch me a lot of money. Okay. So, basically the way the process has to be operated, the way the reactor has to be operated, you have to make sure that C3 is limiting, propylene is limiting, so that the side reaction is as small as possible. If the two basic reactants are C3 and C6, what that means is that the reactor has to be operated in excess benzene environment, so that C3 is limited. If the benzene environment is excess, what that will make sure is that the C12 formation is small. Okay. Okay. Now, the process flow sheet is very straightforward. You have C3 coming in, fresh C3, fresh C6 coming in, C6 is mixed with recycled benzene, this is recycled benzene, and you send it to a vaporizer where heat is put in to vaporize the liquid. This is preheated in a feed effluent heat exchanger. This is the feed effluent heat exchanger. What does the feed effluent heat exchanger do? It takes the hot reactor effluent, and that hot reactor effluent is used to preheat the cold feed to the reactor. Then you have a furnace that heats the feed to the desired reactor temperature, and actually the reaction temperature is quite high, 320, 330 degrees Celsius. The reactor is a shell and tube heat exchanger with catalyst loaded tubes, and it is cooled by circulating coolant at a very high rate on the shell side. So, what that means is that the shell side temperature is essentially constant. Okay. This is what is being shown here. The reactor effluent is actually its pressure is reduced from the reaction section to the separation section pressure. It is cooled in a condenser to liquefy everything that can be liquefied, which is basically C6, C9 and C12. This is fed to a purge column, and what does the purge column do? It takes out the C3 up the top, and all the liquid basically the C6, C9 and C12 go down the bottom. So, this will be C9, C6 and C12, all of this goes down the bottom. And in the recycle column, what you do is you take out the C6 up the top, C9 and C12 go down the bottom, the C6 is recycled back because it is precious, the C9 and C12 are sent to a product column where you take out C9 up the top and C12 down the bottoms. Okay. So, this is the basic process, and well, this is just a base case that we had. Now, if I am given a throughput, so the throughput is given, and I optimize the degrees of freedom that I have, what I find is V2 max should be active, the column should be operated at maximum boil up, P reactor max should be active, and also this should be active. That means the purity of the C9 should be as small as possible. Okay. What does V2 max do? If V2 max is high, the higher the boil up, let me just show it to you, the higher the boil up, the higher the recycle rate. If the recycle rate is higher, then what that means is the excess benzene in the reactor is higher. What that means is the DIPB rate is suppressed as much as possible. Yeah. So this makes sense. P reactor max, well, P reactor max is maximum because as you increase the reactor pressure, the rate of reaction of the main reaction and the rate of reaction of the side reaction goes up by the same amount. You know, the ratio of the main reaction and the ratio of the main reaction rate is to the side reaction rate remains the same regardless of pressure. So what you have is you get an increase in conversion, but you do not have any selectivity penalty. On the other hand, if you change temperature, the rate of the side reaction, if you increase the temperature, the rate of the side reaction increases faster than the rate of the main reaction. So when you increase temperature, you have a selectivity penalty, conversion goes up, but then more of the junk product which is C12 gets formed. So it makes sense that you are maximizing conversion by maximizing reactor without any selectivity penalty. So this also makes sense. What about this chap? This is legal adulteration. If your cumene product should be 99.9% pure, let us say, then I can have 0.1% impurity. I would be a fool to sell, for example, 99.95% pure. So what that means is, what are the impurities? The impurities here are benzene and DIPB. So if 0.1% is benzene and DIPB, benzene is much cheaper than C9. So I sell cheap benzene for the price of cumene. Similarly, DIPB does not fetch me any premium. So I sell cheap or useless DIPB for the price of cumene, right. So I would like this to be, I would like the impurity in the product to be as high as permissible, which basically means that the purity, minimum purity constraint is active. So these three constraints we have sort of understood. Okay. Now what else is going to be economically important? Let us just think about that. I want T vent to be as small as possible. Why? Because the lower the temperature, the lesser the benzene loss up the top. Because you see, benzene is volatile, C6 is volatile, this is basically C3, and the principal impurity in this will be with some amount of C6. The lower the temperature of the condenser, the lower will be my benzene loss. So basically I say that, okay, my vent temperature is basically set by cooling water. So let us say cooling water is available at, I do not know, maybe 40 degrees Celsius, 35 degrees Celsius, then I will say, okay, my vent temperature is about 50 degrees Celsius and not 60, 70, 80 degrees Celsius, because at 50 degrees Celsius I have sufficient driving force in my condenser, 15 degrees Celsius driving force in the condenser, and that basically ensures that I am running my condenser at as low a temperature as possible, so that my benzene loss is as small as possible. And benzene is precious, I pay money, any benzene that gets lost here does not fetch me any money, whereas I pay money to for benzene. Okay. So benzene is precious. To minimize the benzene loss, this should be as small as possible, and this is set by the cooling water temperature. Okay. L2 by B1, L2 by B1, the reflux ratio on the recycle column, it should be high enough so that you do not get too much cumene leaking. You see, cumene is the impurity in the distillate is C6, the impurity is then C9. So cumene is the impurity, because if too much cumene leaks out, then what will happen is that cumene, extra cumene will actually form DIPB from the reaction chemistry, because cumene, propylene adds on to cumene to give you DIPB. So if you have more cumene in the inlet of the reactor, obviously you will get more DIPB formation rate. That does not mean that the cumene should be very small, because if you try to minimize, if you keep increasing the reflux to feed ratio of the column, what will happen is the cumene leaking up, its percentage, mole fraction of the cumene that is leaking out will keep going down. But if reflux is increasing, if reflux rate is increasing, what that will mean is that the boil up is also increasing. So there is actually some kind of an optimum, and basically what you want to do is that this L2 by B1 should be high enough so that C9 does not leak up the top. Too much C9 does not leak up the top. So that is basically this chap, what this chap is doing. What about this chap? Well, you need to hold a tray temperature here constant, you need to make sure that no C3 leaks out here, because any C3 leak that leaks out here will essentially accumulate here in the benzene recycle loop. So you do not really want too much C3 leaking out, because if too much C3 leaks out, then it is going to accumulate in the C9 loop. And what about the tea cooler? Yeah, well, you want the tea cooler to be reasonably, the temperature of this guy to be reasonable, so that all the condensables are condensed, but you do not want it to be so cold, you do not want too much subcooling, because then what that means is this feed is cold, and if this feed is cold, then your boil up here will increase, because to heat up the cold feed, to boil the cold feed will require heat, and the only host is this reboil here. So, you want to make sure that you have chosen your cooler temperature properly, so that you are in the two phase region where C9, C6 and C12 condense, and that is about it. Okay. Now what else? Okay, now let us go further. So, we have got feed is fixed 1, 3 active constraints, that is 1 plus 3 4, these 4 things I have just explained, that makes it 8, and what that leaves are 4 unconstrained degrees of freedom, which are economically quite important, and I will tell you why they are economically important, and these are put here. Okay. Temperature of the stripping section on the column. Why is this important? Because the main impurity here is C9, and you do not want too much C9 to be going out, because then what that means is I am losing product down a waste stream, not charging any money for it. On the other hand, every molecule of C9 that I leak here, I am consuming 1 molecule of C6 and 1 molecule of C3, right. So, I do not want too much C9 leaking down. So, therefore, holding a temperature in the product column at an appropriate value is important, because cumene leaking down the bottoms comes with an economic penalty. Okay, that makes sense. What about the temperature of the reactor and the reactor shell temperature? Well, these two things are important, because if the reactor is too cold, basically if the reactor is too cold, what will happen is you will not have C. So, if the reactor is too cold, then there will be unreacted propylene, the conversion will not be 100%, and there will be unreacted propylene, and that unreacted propylene will basically go out here. So, I do not want the reactor to be too cold, because then I will lose precious cumene up the top of the purge column of the first column. Yeah. On the other hand, if I increase the temperature too much, what will happen? If the temperature is too high, then I will be producing too much of C12. Yeah. And therefore, you have to choose the right inlet temperature and the right shell temperature, so that the reactor is neither too hot for proper selectivity nor too cold to ensure that all of the propylene that you are putting in gets consumed. Okay. So, these two things are economically important. This is economically important, this is also economically important, okay, to ensure the right balance between selectivity and conversion. Basically, you want near complete conversion, and you do not want selectivity to be too low. Okay. So, I have explained 1, 2, 3, which is the fourth thing. Yeah. Well, the fourth chap is this, and this effect I need to explain a little. Okay. You see, what are the impurities in the product? The impurities in the product are C6 plus X C12, and I would like this sum to be 0.1%, because my product is to be 99.9% pure. So, between these two C6 and C12 impurities in the product, only one is independent. If I choose X C6 as independent, that means if I set C6 equal to, let us say, 0.05%, then X C12 will be 0.1 minus 0.05, 0.05%. Yeah. If I choose X C6 to be 0.08%, then X C12 will be 0.02%. Now, why is this economically important? It is economically important because V2 max is active for selectivity. If I try to increase throughput, what happens is this one also goes active. Okay. And what that means is, well, let us see, how do I put it? What that means is that how much impurity level I allow here sets how much impurity level I allow here, that sets how much steam I consume here. So, my steam consumption here the total steam consumption is this plus this, you know, the boil up here plus the boil up here. If I make C6 too small, then what that will do is this will go too high. If I make C6 too large, what that will do is XC12 will be too small and then this will blow up. Yeah. So, either ways I will get a blow up in the energy consumption per kg product. Since I do not want that, this XC6 has to be chosen properly, and it turns out that if you have XC6 and XC12 to be comparable, then you are at the right balance where this is not blowing up or this is not blowing up. Yeah. So, that is why XC6 is important. So, I have explained the 4 things that needed to be explained. So, 8 degrees of freedom were taken care of, and now I explained you 1, 2, 3, 4 other things that need to be taken care of. That has taken care of all the 12 steady state degrees of freedom.